Okay, so in chapters 12, 13, and 14, what we looked at was we did regression models with what? With one quantitative x predictor, an x variable, one quantitative. For example, you had height, and one binary, what sport, like whether the person was a sumo wrestler or an NBA player. That was a quantitative was height, binary was the type of sport, predicting what? Those were predicting a quantitative variable, weight. So we had this predicting a quantitative. But now we're going to look at two, let me zoom out a little bit. Now we're going to look at two binary predictors. So not a quantitative and binary, but two binary predictors predicting a quantitative. Okay, so that's what we're doing here. It's actually much simpler. And the reason I'm introducing it here is because it's very intuitive what an interaction term means in this context. So it's the very simplest setting. So two binary explanatory variables, also called, you could think of them as, they're also referred to as categorical variables, factor variables. They just have, they're binary because there's just two categories, 0 and 1. And a quantitative response, all right? This is a simple case of what you're going to later see is called two-way ANOVA. That's to come. Okay, so here's an example that, so suppose that you're trying to predict the sweetness of coffee on some measure. You have some quantitative measurement of how sweet the coffee is, and you have two predictor variables, two explanatory variables that are, and one is whether you add sugar or not, or just not how much sugar, but just whether you add sugar or not, and the other is whether you stir or not. So that's why they're binary variables. And does this model need an interaction term? In other words, can it be fully explained by just saying, oh, you added sugar, and yes, no, did you stir? Well, is there an interactive effect? Yes, because adding sugar alone is not going to affect the sweetness very much if you don't stir it, and stirring alone without adding the sugar is not going to affect the sweetness. So either one alone doesn't do anything. So yeah, there's an interactive effect. The two of them together are more than the sum of their parts. We have to add a multiplicative term. You just can't sum the effect of sugar alone and the effect of stirring alone. We have to, they have a together. They're more than the sum of their parts, okay? And does the model need another variable? Well, actually it does. Order would matter because we're assuming here that you're stirring second. If you stir, even if you have both sugar and stirring together, the order matters. If you stir first and then add the sugar, it's not going to do anything. So yes, order matters. Stirring first won't affect sweetness. So we really should have another variable. I mean, we use interactive effects in our everyday language all the time, thinking that an interactive effect is an effect that's more or less than the sum of the parts, the separate parts. So, for example, when you fall in love, right? You say there's a huge interaction going on there. You with that person together are your partner. You're more than either one of you are on standing alone, right? Isn't that the truth, though? That's how I feel for sure with my husband. I mean, me alone would be hopeless, and I don't know about him alone, but together it's like really magic. So that's an interaction, okay? You understand? And then it can work the other way too. I mean, have you ever had a coworker where you can do work fine on your own? The coworker might or might not be able to do fine, but together it's like you don't accomplish anything. That has happened to me. I shouldn't even bring that up. But, and the opposite. You can have a coworker like I do right now, my goodness, and it's just like, it's the, you know, it's like the marriage at the workplace. You know, you can accomplish huge things. So like our independent study, like developing this course, I've got a lot of help from one Carly Lasko. Some of you have had her. She's a coworker. We're more than the sum of our parts. So I'm sure, so that's how you can think of an interaction. Okay? Does it make sense? All right. So let's say, but that's the example in drugs. So suppose subjects are divided randomly into 4 groups: drug A alone, drug B alone, both, and neither. And the duration of the disease was recorded. All right. So we have this quantitative variable, y, and we have 2 binary variables. You have drug A coded 1 if given, 0 if not, and drug B, x2, coded 1 if given, 0 if not. And let's say there's no interaction. What that means is that the effect of the 2 drugs just equals the sum of their parts. So for example, if we look at this model here, it says how many days your disease lasts. Let's say it was a cold. How many days your cold lasts without any drugs, when you have no drugs, is 10. And then drug A will reduce it by 4 days down to 6. And then drug B minus 4 down to 6. And then drug B will reduce it by another 2 days, 6, and you get 4. So the idea would be, if you graph this, you'd get parallel lines. You'd have the same slope. What do I mean by that? Okay, so let's put drug A on this axis, and you have either none of the drug or you have the drug. We're not talking about different doses. We're just saying, is it absent or present? Right? And then and let's look at this condition right here, where B is 0. No drug B is involved. Okay, so when it's absent, you're up here at 10. This is your response variable. So this is your response. In this case, number of days this cold is going to last. All right, and we're at 10. And then what happens is when you're given the drug, you go down, the slope is down 4 over 1 and down 4. So wherever that is, it's a 6. Okay? And so this, you can draw this line and say this is when what? B equals 0. And now, how about when B equals 1? Well, all right, so here we have no A, see, no A, but you do have B. And so when B equals 1, we're going to draw another line. Without A, you're right here. So B, the effect of B right here is that it decreases the number of days by 2. So when you have B, you're down here at 8 without A, right? And then you add A in, and you go down to 4, right? Minus 4. And so you go down and you have these parallel slopes. And this is when B equals 1. So you have parallel lines. No interaction effect. All right, so it's just the sum of the effects. Okay, so you take A, you go down by 4. You take B, you go down by another 2. 4 and 2, so you go down by 6. From 10 to 4. 10 minus 4 is 6. 6 minus 2 is 4. It's very simple additive effects. Okay, now what happens when there's an interaction? It means that you don't have that simple additive effect. You don't have parallel lines. When you take both of them, this is in the case where you both have B is 1 and A is 1, it's going to be a non-parallel slope. Either it'll have a synergistic effect and help you, like make your cold go away faster, go maybe all the way down to here, or make you worse and make your cold last a long time. So it just doesn't have the same effect for different levels of the other variable. So here's an example, and you have what's called a non-additive model. You have to add this interaction term. So the effect of the two drugs combined is better than the sum of their parts. If it's better in this case, that means your cold goes away. So it's going to go down like this. So let's draw this. All right. So I'm just leaving it open here for you. So basically we can do the same thing. I haven't put in how strong an interaction effect it is. But the idea is this. A, and it goes from 0 to 1, right? And the effect of A, we're still having the same additive effects. You start off at 10, and you go to 6. So we still have that, 10 and 6, and of course you still, just B alone takes you down to there. But instead of this, having the same, you don't have that. That would be none, would take us down to 4. I'm just going to dot it in, the same thing that we had there. This is when B is equal to 1. No, it's going to either go up or down. And in this case, it says what? Better. So we want our cold to go away. So let's make it go down. Let's make it go down all the way down to there. Let's say to 1 day. So then what do we have? So we have 6 to 4 is 2, and then we're adding another effect, right? 6 minus 2. We should get down to 4, but let's make it go down all the way to 1. If we made it go all the way down to 1, then what would we have to do? We'd have to, 6 minus 2 is 4, and then we'd have to subtract 3. That would be our interaction effect, minus 3. This distance right here between 4 minus 1 is negative. See, you're going down by 3. 2. This takes you down 2, etc. Or you could look at it this way. Okay, so you could say, all right, 10 minus 4 equals 6. 8 minus 4 would have given you 4, but you have to go down another 3. Does that make sense? I could have put anything in here lower, except I don't think you can make your cold have a negative amount. So any number between 0 and, well, you know, go down whatever, any between, can't go down to 4. I mean, it's going to be 4. I can't go past 4. So between 0 and 4. Does that make sense? All right, so let's do this one. Here, maybe I'll just make something up. Let's say I put 11 in here. Now, what are you going to put in here? Okay, so we can do the same thing. So we can go from 0 to 1, right? And 10 and 6. And now, instead of having, I'll just put this one in, 8, just so you can see, this would have taken us to 4 with no interaction. And now what do we want to do? Make it worse? Okay, so we want to have it go up like that. Let's have it go up all the way to 11 then. So that's what we're going to do. We're going to have it go up all the way to 11. So here we would have gone down. So what's from 4 to 11? 4 to 11 is 7. So we're going to have to add 7 here. I mean, we would have gotten 4 without anything, right? 6 minus 2 would have gotten us to 4. And 8 minus what? In this direction, 8 minus 4 would have gotten us to 4. So all we're saying is 4 plus what equals 11. And that's the interaction effect. With no interaction, this is no interaction. And what do we have to we get down to there, but now we have an interaction. Does that make sense? Mm-hmm. Yeah, go ahead.
So where did you get the 11 from?
I just made that up.
Oh, okay. Okay.
I just made it up. I mean, because you could choose any numbers. I just wanted these to match. I could have given you this. I could have given you another number. What if I'd given you 15? What if I'd given you 100? It makes your code last for a long, long time. Then you'd just say 4 plus what equals 100. Does that make sense?
Yeah.
Yeah, that is confusing. I was just... Does that make sense now? Good question. You know what? I think it's much, much easier if you just work on some problems yourself. So let's turn the page, and you'll understand it by... It's like a game. I can explain the rules to you, but unless you start playing, you probably don't get a good feel for it. I hate when people do that with me. I mean, teaching's like explaining, kind of like explaining the rules. Don't you just, I mean, I can never learn a game by somebody just saying, okay, here's the rules, you know, especially some complicated card game or something and just laying them out. No, it's like you have to play it. And then you understand as you go along, and you really do understand why the rules make sense, etc. So why don't you guys just, okay, so let's see what I'm saying here. Suppose A and B are two treatments designed to boost scores on some exam. Coded 1 if given and 0 if not. Okay, so two study methods. Now, fill in the blanks below so the model, like here it has no interaction, and the data match. All right? And these two, I made a mistake here though, so let me just see. This should be a 20 and a 30. So you can correct that. And if you want to just, I'll give you a few minutes, but if you want to go ahead, I just realized that I left out a row here. So if B equals 1, so what happens there? And so what are you supposed to do here? I want you to like fill in the blank and also come up with the model. Here, I gave you the model. That's a 20. All right. So just start this and talk to each other, and then we'll get, you know, just I'll come back and we'll do it together. But it's so much better if you just plunge in and just try it.
Are the boxes for the one you changed supposed to be 20 and 30 also? For the one you changed to 20 and 30?
This should be...
But inside the boxes too?
No, everything's right, except these are disagreeing. That's why I had to do it. 5 plus 20, if you put a 1 in here, is 25. That's why I changed it. Okay? So just work, you can talk to each other, and I'll just give you a few minutes, just make some headway, and then I'm going to go out and get a drink of water. I'll be right back. Okay, look up if you're finished so I can get a feel for how people are doing. Okay, so let's look at it together now. All right, so for this first one, I hope you all got 50 here. You're just saying, okay, it's just a complete additive effect. If you put 1, this box is a 1 for A and a 1 for B, so you could just say 20 plus 30. There's no interaction effect, so you add 20 here. And then 30. See, we're just saying this right here says, okay, when you go from 0B, this is all 0B across here, you just add 30. whether A is present or not. Does that make sense? Or you could think of it as this right here. Horizontally, you add 20. 0 plus 20. Whether plus 20. Whether B is present or not. Okay? Does that make sense? All right, so that's an easy one. Now we have the same thing, but we're not going to get 50 here. That's 50. Look at this. We would have gotten 50 with no interaction, just by the added effects, 20 plus 30. But no, we got 60. So we have to say 50 plus what's our interaction effect? 10 to get that. And then you can check it by saying, okay, when you're in this box here, your A value is 1 and your B value is 1. So you can put a 1 in for A, a 1 in for B, 1 times 1, and make sure it all adds up. 20 plus 30 plus 10 is 60. Okay. Now, no interaction term. Well, that just means we have an additive effect. When you go from 2 plus, here you get to 2 plus 8, and it should have the equals, look what I just did, 2 plus 6 equals 8. If there was a 0 there, we started with an intercept here. When you don't give any drug, there's still an effect of 2. So 2 plus 6, so A, if we're going to call it the boost in exam scores, we had intercept, we started at 2. And now, when we add A, we get 6. When we add A, when A is 1, right? And now, how about when we add B? When we add B, we get an effect of 8 times B. And there's no interaction effect, so that's just going to be 2 plus 6 plus 8 is 16. And you can see 2 plus 6, there's our parallel slopes. 2 plus 6 equals 8, and 10 plus 6 equals 16. Or conversely, the same when you're looking at the change in B, 2 plus 8 is 10, and 8 plus 8 is 16. Does this make sense to people now? Okay, I see some nods now. All right, so this is, what did people get here? No interaction effect, so this is very easy. What do? We say if there's no interaction effect, it's going to be 5 plus 25 plus 35, right? Another way you can look at it is, all right, this 30 adds 30 there. So we'll add 30 there, making it 55. Or conversely, you could just say the 5 plus 20 adds 25. So it has to add 20 here. Does that make sense? Okay, so now let's see. We are down here. Now we got this same thing here. And what are we doing here? All right, so what should we fill in here? This right here tells you when A equals 0, this is the effect of B. This is the effect of B, right? So we're just going to add 30. So we know how to fill that in. That's easy. This right here is the coefficient of A, and this right here is the coefficient of B. Now, if there's an interaction effect, without an interaction effect, we would get 50, right? So you might want to pencil that in. Without an interaction effect, we'd get 50, right? Does everybody see that? But we didn't get 50. This is telling us to add this interaction effect, minus 10. So we should get 40. And of course, you can just always check it. Just put 1s in for both A and B. Because when you're in this spot right here, which is the only sort of difficult one to figure out, you just put a 1 in for A and B, and you get 20 plus 30, and you put minus 10 is 40. All right. And we can go on, and what's this? All right, so right here is when there's no A or B, right? That's just our intercept here. No A or B is involved. The response is 10, right? Now, how do we get the response of A? When you go from 0 to 1, you go from 10 plus 2 equals 12, so that has to be 2. When you go from 10 to 15, B equals 0 to 1, you have to add 5. So that has to be 5. Now, without an interaction effect, that would mean that I'd get 10 plus 2 plus 5 is 17, right? Or 15 plus 2 equals 17. Or 12 plus 5 equals 7. So I should get, it would be 17 with no interaction. But I didn't get 17. I got what? So I got, how did I get 9? By subtracting off 8. So that has to be minus 8. And you can always check it by putting 1s in for everything and make sure you do get 9. All right. And here I think everything's the same, 10, 12, and 15. So everything's exactly the same reasoning. 10, you had 2 there, you had 5 there, and we should get 17. But we didn't. We got 20. So 17 plus what equals 20, so that has to be 3. All right, so questions on that? It's just easier to understand interactions in this context. It's the easiest way. Sometimes people get confused in other contexts. Yeah.
I'm confused on the last two parts.
On these two?
Yeah.
So, okay, so you're confused. Do you know how to get that?
Yeah.
Do you know how to get that?
It was the last two.
Do you know how to get this one? Oh, you don't know how to get this one? Okay, so how do you get the coefficient from B? Just the change. When you add B, here you have B 0. When you go from, we're not even talking, A is out of the picture. We're just talking about when A is 0, right? So we're just saying what happens when you could put everything equals to 0. How do you get from 10 to 15? You have to do it by adding 5. Maybe you forget that when B is present, you see it's equal to 1. So if you look in this box, you can see exactly what A and B are. You could just, A is 0 here. So you could if you could pencil in like a 0 here if you wanted. If you wanted to figure out this box, and that would make this 0. So a 10, and this is a 1. So it has to be 5 to get 15. Does that make sense? Now how do we get this one? You could say, okay, in this box, A and B are both 1. So you can pencil in 1 here, a 1 here, which make a 1 here. And we got 9. So you say 10 plus 2 plus 5 is 17. And this is going to be 17, and I want to get down to 9. So 17 minus 8 is 9. Does that make more sense? Okay. Any other questions? Okay, so now we are going to move to our next part, part 5, on multiple regression. Now we've been doing multiple regression. I should say this is multiple regression with quantitative predictors, with more than one quantitative predictor, with 2 or more quantitative x's. Not any binaries here. We're going to just look at multiple quantitative predictors with quantitative predictors or explanatory variables. We've been doing multiple regression, but we've been doing them in a simpler case where one of them is just categorical, a binary one, so that we can visualize it better. And the last thing we did was 2 binary. All right? So now we're going to look at this. And we've already, the model looks the same. It's just, oops. If you have a hat on one of these, it means a predictor. I should have a hat on all of them. Here I'm adding an error bar on them. Okay. Sorry, this is just a typo. Okay, so here's the simple regression. Now, just to refresh your memory, this is just like y equals mx plus b, but this is the m, the slope, and that's the b, the intercept. So we're just saying that we're calling the intercept beta not, and if it's something that we're predicting from our sample, we put a little hat over it. And if we're estimating the average, or saying what the ideal model is, we don't put the hats on. And then we have to add some error term. Okay, so here we're making, a particular prediction. Here we're saying this is our model, and of course our model isn't perfect, so there's error around it. So now what are we doing here? So this was our notation I've already introduced. Intercept you put first, and there we have one slope and one x. With one x, you don't necessarily have to could put it 1x. But now we've already done this, but the difference is that these x's now are both quantitative. I'm sorry, I forgot the hats. So they're both quantitative. Okay, we've already seen that these slopes in our multiple regression equation, when we did it with one binary and one, in all our previous chapters, one binary and one quantitative, we worked it out, are not the same as those in simple regression. And now we're going to see the same effect. It's just a little more difficult to understand just because we can't split one of these variables. We can't stratify it into just two categories and completely capture all the possibilities. They're both quantitative. So we'd have to split it into lots of categories. For example, what are we doing here? We're looking at homework and exams, predicting what you're going to get on the final. So it's not just a 0-1 variable that we can completely describe by saying, oh, did you do the homework or did you not? That would be a binary variable. But here we're looking at the actual score of the homework. That's the difference. So we can't just split it into two graphs. So it's a little more complicated, but the ideas are just the same, and the slopes from the simple regression equations change, and you'll see how when you put them in the multiple. All right, so just to refresh your memory, we know that the correlation between two sets of numbers, like when we have simple regression, the correlation between two is defined as what? You change both variables to z-score, that's standard measuring stick, right? So change them both to z-scores, and then you multiply the z-scores together and take the sum of those products, and then take the average. So it's the average of those products, Cx times C1. And correlation, as you know, ranges from -1 to 1. All right, so how do we define correlation? What does this multiple correlation coefficient, R, mean when we move to multiple regression? We already looked at it in simple regression, and we said, okay, what is it? We said it's just the absolute value of R, the positive R. But what does it mean? Well, for multiple regression, it's the correlation between your actual Y values and your predicted Y values based on your model. This is the only type of correlation that makes sense when we have more than one X variable, since correlation is only defined between two sets of numbers. You can't, what does it mean? Not 3 or more. You can't define it between 3 or more. It's defined between the correlation between two sets of numbers. So we have two sets of numbers. We have the predicted Ys, and we have the actual Ys. And it makes sense that, thinking of it that way, that for simple regression, it's the same thing as the correlation coefficient, and it's the same thing as the positive correlation coefficient. It can only be positive since our predicted Ys are always positively correlated with our actual Ys. I mean, the predicted Ys, our X and Y, can be negatively correlated, but we're going to make a prediction as close as possible to our actual values. So that we're not going to make the opposite prediction. If they're up, we're going to make it, if it's a negative correlation, we'll still get as close as possible to our predictions. So otherwise, we just reverse the sign. So we're not going to predict the opposite. So they're always positively correlated. Now, suppose we wanted to predict final scores from homeworks and exams using this form. Let's think about what we need to do. Okay, there's also these 4 simple regressions. Between what? Between homework predicting final, between exams predicting final. Those are obvious, right? And now we're combining them. But then we also have to consider the correlation between these two. Between homework and exams, what the correlation is there. So we really have 3 little r's here that are not the same as big R. Okay, so how are they going to factor in? So let's turn the page. Let's go. So let's just look at the 2 predictor variables, the x1 and the x2, predicting y. So we're both predicting finals here. And let's just look at them separately. So here you have homework predicting final, and here you have exams predicting final. This is from our data set called the Grades Online that we've already worked with, the 107 data points. You can look it up. That's where I got these from. Okay, so both of them show a positive trend, which you'd expect. And here's your correlation. As you'd expect, wouldn't you think that exams would be better predictors of finals than homework would be? Don't you think? I mean, final is an exam, so it's going to be, some of it's just your exam taking ability is going to be a better predictor rather than your homework doing. But they're both positively correlated. Now, so why would we even want to put them together? Why can't we just look at these separately? What do we gain by putting them together? Well, we can certainly make a better prediction for the final if we combine information about 2 predictors, right? That's going to give us a better than either one alone would. And we can also, this is more importantly, we can look at the effect of each predictor while controlling for the other predictor. In other words, keeping the other predictor constant. That's what it means to include a variable, an independent variable in a multiple regression. It's like, how much do you add after we've controlled? For example, let's say here's our regression equation right here. And if we want to add homework in, we're not going to use that same slope here because what we're trying to do is explain or predict finals after we factor out the exams. How much does homework help? How much is our prediction for final going to help if we add homework here? And since homework and exams are somewhat correlated, it's not going to help as much as what it does here because this includes the effect of exams. I mean, think of it this way. My right foot, or your right foot, is anybody's right foot, is a very good predictor of height, right? So you can get, and your left foot is also a very good predictor of height. So you could have height on this axis. We could have a regression equation, left foot, right foot. But then if we put those 2 together, it's not going to help our prediction anymore if we put the right foot and the left foot together because they're explaining almost entirely the same thing. So adding the extra foot would just what it means by controlling for the other variable means that you're just going to add the part of your left foot that helps after you've already predicted your height from my right foot. Does adding my left foot into the mix help at all? It doesn't, so it wouldn't. Does that make sense? But my right foot predicts my height, but you also might say, okay, what else would predict my height? Let's just do weight. Weight's a better one. So my right foot side is predictive of weight. So like bigger the foot, generally people weigh more. But then if I added another variable like my height in, that would help more. Does that make sense? Does it? Yeah, it's just giving some independent information. Okay, so you'll see this. And this looks awful. Why? All right. What are we talking about? Exams and homework. Let's get back to this. All right. So y'all understand this. Let's look at this. All right. So, how about a picture? It's worth 1,000 words, I think. So, the question is this. In multiple, okay, so we've got these two slopes. You see these two slopes? This is what I'm trying to explain. This slope is not the same as this slope. You see? When you combine home and this one is not the same as that. That's what I'm trying to explain here. All right? And these slopes are kind of hard to calculate. So we're going to let the computer software do it. Calculate it since we'd have to adjust for the R's and the SD's. I mean, I'll do a little bit of it, but it's pretty complicated. And the calculations are tedious, and it's much easier if you've know matrix algebra. So if you want to see it, I'd be happy to, and you'll learn it in upper level courses, and I can put it as an appendix if you want. I'll work it out. But first, let's just understand the idea. I'll work it out just a few times, but the computer software is going to be giving this to you. All right. Now, do we have the same slopes as we did? No, we just showed that we don't. And now, why do the slopes change? This is what I want to explain. Well, I explained it in words, but I think the best thing is a picture. So, why do the slopes change? They change because, okay, you have exams. Let's just say this is the effect of exams predicting the final. And you also have a littler effect. I could make a smaller circle for homework. And if these two were uncorrelated, if knowing somebody's exam score couldn't tell you anything about their homework and vice versa, then they wouldn't change. They'd be two separate little circles, both predicting finals. But obviously, knowing something about your homework does correlate with your exams. People who have higher exam scores also have higher homework scores. So there's an overlap here. It's a littler effect. I'm drawing a little circle, and this is homework. Now, you see that little overlap? We'd be double counting if we just, that's a double counting. If we just plug these two slopes in here, this is the effect right here. Right? If we just copy it down and said, okay, and I'll put the effect of exams in right here, we'd be describing the situation where they were uncorrelated, where they looked like this, homework and exams. Then that would be perfectly fine, predicting finals. Can you even read that? But if they're uncorrelated, which they're not, then yeah, they're not going to change. But we're in the situation where they're correlated. And so they're both predicting finals. That says homework's predicting a final. That says exams. And if they didn't change, why did the slopes change? If they didn't, we'd be double counting. Since homeworks and exams are correlated. They're not independent effects. So that's the whole point. And so if we're in this situation, when they're uncorrelated, they don't change. You get exactly the same. So they change because they take into account how the homework and the exam averages are correlated. Here's the correlation matrix showing all three variables. So you have the x1, the x2, and here's your y, the x1, the x2, and here's your y. And obviously along the diagonal, they're all ones because x1 and x1 homework is perfectly correlated with homework. Exams are perfectly correlated. That has to be one along the diagonal. And now it's totally symmetrical. Why? Because here's the correlation right here between homework and exams. That's between your two x variables. If this was 0, if the x1 correlation with x2, if these and x2 with x1, obviously these are all symmetrical across here because they're the same variables. These have to be, symmetrical. So if the x1 next to, if that was a 0, and x1 next to that was a 0, then the slopes wouldn't change. They'd be two independent factors. They'd contribute the same. It wouldn't matter if the other one was in there. So that's the basic idea for multiple regression. It's separating out the effects of the two variables. When you add another variable, you're saying, okay, does it improve my prediction after I've factored out? Does it add anything to it? And it doesn't add the correlated part, it just adds the other part. They're called partial slopes sometimes. All right, so let's work on how we're going to figure these out. So here's what I'm talking about. Here's this correlation. You can see the correlation between the two x variables, exams and homework. So this is the third correlation that has to be taken into account. Why? This is x1 predicting y, x2 predicting y, and then x1 predicting x2. So that's what we have here. So how do we, what is this? Did we get this equation? We can get this equation. We got this from the correlation matrix. See? That's just right here. So we got this from the correlation matrix. That will be given, it will be given to you. And we could, just from the information, I'm going to ask you to do this, so let's walk through the steps of how I got this equation, or just how I got this slope. That's what I want you to focus on. So how do you get that slope? Well, you're given, where are you given this? Oh, here. If I give you all the averages and the standard deviations, then all I'm doing, I can just, the SDY over SDX, that's what I need. So we're predicting, what are we predicting from what? In this instance, we're predicting exams from homework. So we're going to have SD9, this will be SDY, and that'll be SDX. All right, so let's do it. So our slope, I just want to show you how to get that slope. These are easy to get in the simple regressions. Those are just going to be R times SDY over SDX. And even though we were calling these both predictors, x1 and x2, in this context, we're going to predict y from x. All right, so our slope is going to be 0.3933 times the ratio of what those SDs we just got. And what was it? The SD for exams, I think. And we had the SD for homework. And one was 9.197 and the other is 11.73. So, which one should go here? Like this? 9.197 and 11.73. And that, if you do that, you should get that. 0.3083. Okay, checks. All right, now, so even though these slopes are going to be given to you, and you're going to have to, it's beyond the scope of this course to actually derive how these betas are computed, but I will post it in the appendix. I'll update that appendix and post everything there. And if you're interested, some people have been coming into office hours and we show them. Happy to do that. You'll do it in your next course, 400 or maybe 420. Oh, I don't know. Once you do, you just need calculus. That's basically it. And matrix algebra, which is why it's required if you guys go in for 400. But, sometimes that doesn't even really help you understand the intuitive picture as much. And also you can work it out. I can show you, I can do it, but it's just kind of tedious and it's much easier. Okay, so let's see if we can do it. So let's focus on why the homework slope decreased. Okay, so why did the homework, and then we can do the exam. So why did the homework go from here to here? You know the picture of why it did because we're subtracting out that correlated part, etc. And, you know, this is a lot of words that I already said. Okay, I already said all these words. How about, can you just answer this without going through it? Can you just, I mean, you should read this on your own, but I don't think there's anything new here. It's just more detailed way to think about it. Is it okay if you read this on your own? I think, but answer this question. Why would the coefficients in the two separate single, when would they be the same as the ones in the multiple? When do you think they'd be the same? We talked about it. When the correlation, let's just write this down, between, when would these, like this stay the same? And same for the other one. Remember what we said, when the correlation between what? The two predictor variables is what? You fill in that blank. They'll stay the same when what? When the correlation between them is what? Just put a number in there. 0, yes, good. Did y'all get that? All right. 0. Okay, so now, all right, so this is my creative way, you won't see this anywhere else, of just showing you without teaching you how to invert a matrix and do all this stuff and take the, how to, without a lot of math, just intuitively how these are arrived at. And I had to really think about it a lot, and I realized that it's a lot easier to start with this full model. I couldn't think of an easy way to take the two simple ones and go to the full, but it's pretty easy to start with this full one and see how you get the simple ones. All right? So we'll do it. So let's just spend the next few minutes, and I'll have you do this on your homework too. So this is just my creative way of showing you how they're related in the simple case with just simple arithmetic in 2 steps. But I couldn't do it in a few steps going the other direction, taking the two simple and getting these. So I'm going to do it in this direction. All right, so you start with this full model, all right? And what are we trying to do? We want to see the relationship between these two. Why aren't they the same? How do we get from here? Is that what we want to do? We want to, yes, we want to look at, we want to see how we get, is that the question? Yeah. Okay. So we're going to start with this full model here, right? And now we want to see where this comes from. Where does that come from, right? Well, so what do we want to do here? We want to express this only in terms of homework, right? I want to get from here to here. So final, well, this is already expressed in terms of homework. That's good. Now, is there any way I can change this to an expression in homework? Can I? Is there, can I rewrite exams equal to an intercept plus something times homework? Yes. That's exactly what we just did on the previous page. So instead of, I'll substitute for exams, that. And then I'll have something totally in terms of homework, which will be that. So this is the part of the homework that's uncorrelated, is to give you the picture. So we just, when you do the multiple regression, it's that part. And now I want to add the correlated part, which I get from the relationship how well homework predicts exams, or vice versa. So let's do that. So I'm just going to, so I'm going to say plus, you can see the steps here, plus 0.5824, and instead of exams, And I can just ignore these intercepts because we're just talking about focusing. The intercept's going to change, but I don't care about that. I just want to show you how the slope changes. So now I'm just going to put in for here, what should I put in? Instead of exams, I want something written in homework. Right? And so this is what exams equals. So I can just stick that in. So I will 0.3083. And then if I add these together, I go through the steps and explain it here, I get exactly it. So if you add 0.1641 plus that, you'll get just that. So I'm just ignoring this intercept because I just want to explain this. This is boring, the intercepts. I just want to explain the slopes. Does that make sense? All right, we can do it. It was real easy because we already figured that out. Let's say we hadn't, which like you might not on your homework. And this explains everything. Because I have to write a textbook. This is the textbook part, which nobody reads, but it really is short. So this is like a textbook part. And I'm even skipping it. Why are textbooks so boring? Even when I wrote it, it's hard for me to read it. But I think you should read it because it's really good. You learn more. But it's really hard to read, isn't it? All right. It's harder to write. Ugh. Okay. Now we go here. So let's do the same thing. I explained. Now let's examine. Let's explain. Let's examine how the slope for homework changes by eliminating how the slope for exams changes. So what am I trying to explain here? I want everything in terms of exams. So this part's cool. That part's good. I just want to change this. So I want to keep this as 0.5824 times exams. And now what do I want to do? I want to change this to something times exams. Well, we're going to have that part, 0.1641, right? And I just want to rewrite this homework as something times exams. All right, so we want to eliminate, do I have to write out the steps? Maybe I should. We want, because you'll understand it now, but then you go back and you say, what did I do? So now this is slowing myself down again. Oh, I hate this. So we want to eliminate what from the picture? We want to eliminate homework. So we need, right? We want to eliminate this homework. So we're going to replace that homework. We're going to substitute in something times exams. Get rid of that homework instead. All right, so that's what we're going to do. And we just have to get that slope. So the slope is equal to r times, why can't I just solve the other equation backwards? I can't. That's not really the slope. You can't just do that because your SDYs and SDXs are going to be flipped. So this is going to be what? Instead of this, it's going to be 0.3933 times, we're just SDY, we're switching SDY and SDX. Okay. So we're going to get 0.3933, and you're going to do this on your homework, and I'm just flipping this, and I can forget about the intercept, and I got 0.5016, and that's what goes in here, and that's going to be 0.5016, and that's what's going to go in here. 0. It's hard for me to read. 506. 0.16. So I'm going to multiply those two together and add it to that. And that'll be my answer, that. So we can do that, and we'll say the final, I'll just write it here because it's hard to read. I'll just write that out here. So your final is equal to 0.164 times your homework. But your homework is 0.5016 times exams, right? You follow so far? I'm just saying, right? You got it? And what? Plus 0.5824 times exams. I mean, all you have to do is that plus that too. I'm just writing it for like later if you forget what you're doing here. Okay? And so when I did it, I multiplied those two out and I got 0.0823 times exams. And I'm adding it to 0.5824 times exams. And it checks, okay, maybe. All right, so these two together equal that. Does that make sense? Mm-hmm. So these are called partial slopes in here. Partial, the part of the exams that explain or predict final after the effect of homework's been factored out. And this is vice versa. And this is the effect of exams of ignoring homework. But people who have high exams also have high homeworks. So you can't just... So this is the part of the exams after the effect of homework has been subtracted out. We're parceling them out and making them separate effects. That's multiple regression. Let's see. So you'll do that on your homework. Do you understand this? This is not too bad doing it this way. I'm just thought it would help you understand what happens in these multiple, what we mean by controlling for the other variable. And what we mean is that for everybody, okay, so for everybody, this slope means that 1 extra point on your exams, on the average, 1 extra will lead to 0.5824 more points on the final for people who have the same exact homework score. So for people, if you just look at people who have exactly 90s on their homework, this is the effect that an extra point on your exams will do. Whereas this doesn't take, says, okay, that includes the effect of homework too. It doesn't stratify by your exam scores. See, this is stratifying for each level of the other variable. Now we're also can have an interaction term because an additional point on your homework for people who have 90s, additional point on your exams for people who have 90 on their homeworks might be different than an additional point on the exams for people who have 60s averages. And that's why we're going to have to add an interaction term. So that's to come. But for now, I think we did tons. And I'll post your homework right away.